All right. Where am I? 11. I've got this graph. Overrated. Just set the tone for the whole day. That's right. We're doing this calculus. Yeah, I was just sketching a graph of it real quick so I have a reference point here. Where's that going at like 3? 3, -3? Something like that. Over 2, 6. Well, maybe they should just put tables together every day because it's a lot later, or else y'all are just scared right now. Bless you, bless you, bless you. All right, here we go. So it says that this is the graph of velocity, yes? All right, so part A says, when does the body, I'm not even going out. When does the body reverse direction? I know. They should be in here too. I'm a bit disappointed in the decision-making process there. You're not wrong. Putting together a table from Ms. Lopez. She asked them, and I said, yes, they can make that decision. And then, when does the body reverse direction? All right, so remember, I'm looking at velocity. So when does velocity indicate a change in direction? Okay, so I'm not going to say at 0 because it could just sit at 0. You'll see some bugs that will start moving along. They'll come down, they'll hit that, and they'll bounce back up. So they're always moving forward. They just, as they get here, they stop, and then they keep moving in that same direction. So when it changes signs, yes? So where does it change signs? At 2 seconds and at, what did y'all say, 7 seconds. Does everybody understand why? Right. So, yeah, when it's below the x-axis. Right. So somebody said no. Look at your red sheet. I'm pretty sure this is on the red sheet. So if you look, initially t equals 0, right? We all know that. When the particle is at rest, that's when velocity equals 0. So resting. Yes, and by resting, it means that my bug who was moving has stopped. Just stopped. Instantaneously stopped. It's not a long stop. It's just a pause, right? All right. Unless it stretches across here, in which case he's resting for an extended time. Okay. He's moving to the right when velocity is positive. Well, where is velocity positive? Here and here. So he's moving right. He's moving right. When is he moving left or backwards or down, depending on which direction? Yeah. Well, that would say an interval from 2 to 7, but we only want to say that it's at, because it says when does it reverse direction, so it's only at that particular second. If you said this says over the interval from 2 to 7 seconds. That would mean during this whole time here, he was changing. He can't change direction. I mean, he'd be going. You see what I'm saying? Yeah. Are you looking at? Tell me what are you still talking about A? Yeah. So A says when does it reverse direction? So when does it change the way it's going? So at first he's moving right. So he's for 2 seconds, and then at 2 seconds he stops, and then he moves backwards from 2 to 6 seconds. So he changes direction at 2 seconds, and then, well, it just depends on the way the problem's written. It doesn't say. Either one's the same thing, though. I always think left, right, unless it tells me otherwise. Right? And then at 7 seconds, he flips back around and he's going right. Or not even flips around. I mean, he stops and then he goes the other way. Does that make sense? Okay, well, yes, if I was looking at position, but here I'm looking at velocity. So velocity in and of itself is speed if we take the absolute value. So if I was talking about speed here, I would need to take this negative part, flip it up, and at any point I could tell what the speed was, right? At 4 seconds, he's going, what, 3 meters per second approximately. The absolute value of velocity, because you can't have a negative speed. That's okay. Um, Part B says, when is the body moving at a constant speed? From 3 to, that's exactly right. Because look, right here, right, he's always going the same speed. Or flipped up here, that's speed. But he's always the same speed. This is velocity. This is not position. So you have to remember what it is you're looking at. That's just an instantaneous, right. And those only count for stopping. And either they reverse direction at that point, or they just rest and then keep going. So he moves right, stops, if this is velocity, stops, then he keeps moving right. So he's done this. He started here and he goes, boop, 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 boop. Oh, stop, I'm going to rest. But instead of reversing whenever I stop here, then he keeps moving right. And then whenever he gets here, that's when he changes direction and goes to the left. So if it crosses over, if you have a sign change, then you've changed direction. If you just have a 0, that just means you stop. But anytime it says, where's the bug at rest, that's every time it's 0. The bug's at rest. Or the particle, yeah. 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 All right, so y'all understand. Okay, so we said approximately when is it moving at constant speed. Graph the body's speed from 0 to 10. We said that's the same thing. The only thing is I take this negative part and I flip it up. Yes? All right, and then part D, graph the acceleration where defined. Okay, so where, and this is where you really have to think about it, where would acceleration not be defined? Tell me the relationship between velocity and acceleration. Acceleration is the derivative of velocity. Where would the derivative of a function fail to exist? At corners, at cuts, at points of discontinuity, right? So on this yellow graph, and try to look through just the yellow, where would acceleration not be defined? 1, 3, 6. So y is 3. Remember what it means to be differentiable. The derivative from the left has to equal the derivative from the right. So the slope as you come in from the left, which would be here, has to equal the slope as you come in here. Yeah. So it's kind of like a corner right there. They meet at that sharp point, right? All right, so all that means is whenever I graph that derivative, just like you did on your quiz, those are going to be open circles because they're not defined. So if I graph acceleration, here's the good part. 2, 4, 6, 8. How am I going to do this? It's a bunch of lines. What kind of lines? Horizontal. How are you going to find where they are? The slope. These are just slopes. These are all lines. These are not curves or anything of the sort. So I can come in. Here. What's the slope? So I'd be up at 3. Start here. It goes to, what's that go to? 1. 1 with an open dot here. Now what's the slope from 1 to 3? From 1 to 3. You couldn't look at it and tell. What could you do? Somebody said it. Or the triangle. That's exactly right, Hannah. How about the slope between 3 and 6? 0. How about the slope between 6 and 8? 3 again. How about the slope between 8 and 10? Should be negative something. Negative 1.5 or negative 3 over 2. They're always closing. You need to find those slopes if it's a line, yes. Because if you get on the FRQ, they'll want you to find that, calculate that value. First and the last are going to be closed. From 8 to 10, they said it was negative 1.5. Is that not right? If you look at your red sheet, obviously we've not done integrals. We will get to that, but save this sheet. This is going to be very important. This is the ones that Robert called and asked me if he could get for his calculus classes at college. Velocity, x. They use x instead of s. Yeah. What? They use x instead of s on here. So when you see x, that's, remember I told you it could be s or x. So they use x on here. That's position. That's all that is. So if you look, this is a nice little check for you if you start, because this gets really confusing when you start pulling everything together and what it is you're looking for and what it's asking you. We haven't, and we're going to talk about this today also, when velocity is increasing and decreasing and what that looks like. And we'll talk about that a little bit more today. Your speed is on here. When your speed is in, we're going to talk about speed increasing and decreasing today also. I think that the only thing I would tell you is displacement does not, it looks like displacement, I forgot to put that on here. They got total distance traveled. But remember, what is displacement? The difference in where you started and where you ended up, right? That's all it is. It's not the total. Yeah, I would write that on there. Displacement there. All right. Approximately. Where you see it, I'm sure that's what it is. Oh, that's an integral. We'll get to that. That's second half of calculus. A couple of things just because I'm right here with it, and then I'll finish your homework problems, I promise. We talked about speed as the absolute value of velocity. This is on your sheet. This also needs to be in your notes. Speed is only increasing. This is almost always a little part of an FRQ2 for some reason. It's only increasing when the sign of acceleration and velocity are the same. Okay? They can both be negative, yeah. There are you take where it ended and where it started and subtract those. Oh, total distance traveled? No, we'll get to that whenever we get to. For right now, what you'd have to do is you'd have to look at every time it stopped, how far did it go, and add those together. In other words, right, I would, from here to here, I could add that all at one time, right? I could say, where was he if this was 0, if this was 5, and if this was 10, and maybe this is 12. I could say, where was he at 0, and where was he at 10, and find that distance, right? But, right. But then I'd have to go in and find 12 also, and I'd have to add that in instead of, because it's going to give me a negative here, because it's moving backwards. So y would be your velocity. That would be how fast it's going. If this was, you would use that equation, that x of t equation, or that s of t equation. Both of these are the same. But we'll get to that in a little bit. Yeah. So the speed, and this is really important because if I'm looking at the graph of velocity, right? And y'all stay with me because this is the, yeah, I'm going to go back to 18 too. But I wanted to say this because I want to relate this back to these ones we're doing also. If I had that graph, what does it look like? This doesn't even have to be exact. If this is velocity, and I said, when is, what's his name? Meriwether. When is Meriwether speeding up based on this graph of velocity? What has to happen? The sign of both acceleration and velocity have to be the same. So let's look at this for just a second. The sign here of velocity I thought that was my phone, and I thought that Russell had gone back home or something, and I was like, okay. Here, from here to here, velocity is positive. Agree or disagree? And from here to here, velocity is negative. And from here to here, velocity is positive, yes? But I've got to match the sign of velocity with the sign of acceleration. Acceleration as it relates to velocity is what? Slope, or the derivative. So, when does the slope change? In other words, as I start here, what does the slope, what is the sign of the slope? So that means acceleration here, positive. Do you agree or disagree? Speed is increasing, why? In this interval right here, both acceleration and velocity have the same sign. Therefore, Meriwether is speeding up. She is hopping. She is moving, right? But then whenever I move over here, what's happening right here with acceleration? It's negative, right? So from this to this, am I speeding up or slowing down? Why? The signs are different, right? Acceleration is negative, but velocity is positive, so I'm slowing down. All right, so speed up. Slow down, but this slow down, I'm going to stop right here because here's another interval, right? Here, acceleration is still negative, but velocity is also negative here. So here, guess what I'm doing? Speeding up again. So even though she's moving backwards, she's moving backwards faster. Right? Are y'all tracking with me? All right. Yeah. How about here? It's not right. She's moving, but she's moving at a constant rate, right? So she's neither speeding up nor slowing down. She's neither, right. She's just moving at a constant what? N or? Could it be still what? Yeah. All right, and then I hit this little part right here. What's acceleration there? Acceleration is positive. Why? The speed is decreasing. Why? Because even though acceleration is positive for this little spot, velocity is negative. Those signs do not match. So it's speed's decreasing. Huh? Because that doesn't matter. It's the signs of the acceleration and the velocity. Because I'm not asking you how fast is it going. I'm not asking you the speed of it. I'm asking you, is it speeding up or slowing? Like, look here. If you are going towards zero from left to right, yes, you would be. But here, you're talking about if I'm coming in towards zero here, yes, but that's not going to be justification. If you're on a justification, is this speeding up or slowing down, then they want you to find, literally, show me acceleration is either positive or negative, and also show me at this exact point velocity is either positive or negative. So here acceleration is positive. Velocity is, so what's the bug doing? Speeding up. Depends on the graph you're looking at. Right now I'm looking at a graph of velocity, so yes. But I could use this same thought process, and we will if I have a position graph, and I have to look at the slope for velocity, and then I have to think about the rate that the slope is changing for the acceleration, which starts to get a little bit harder, but we'll get there. All right, how about this last little piece? You tell me speeding up, slowing down. Slowing down. Because even though velocity is positive, acceleration there is negative. Does that make sense to everybody? Okay, that's also on your sheet. Yes, the derivative. All right. Yes, no, maybe so. Maybe so, leaning towards yes. It's hard to interpret from the graphs. And right now, looking at the graph of velocity is a little bit easier than when we look at the graph of position and have to infer all this stuff. I'm assuming y'all have a question about the rocket one. Every year I have to work the rocket one. And which one? 11 what? D, the graph. There's the graph. This was at 3, -3. Are you talking about where they are? Yeah. This was the only one that wasn't at 3. It was at like -1.5, I think. Does that make sense? Yeah, just like you did on this quiz. You take the graph and graph it. All right. We did okay on 10. Good. Make sure you look. 10 is the graph of position. It's not the graph of velocity. B was graph the particle's velocity and speed. So again, this was a derivative graph, right? I take the derivative of that that's given and I graph it, and that is my velocity. Let's see, it looks something like this. Y'all have to look on yours. I'm not going to put the exact points on here. This is 10. This is 6, -4. This is position. You feel like they got what wrong? Because this is position, not velocity. If 1 second, if he's right here and then a second later he's still in the same spot, what's going on? He hasn't moved. He's standing still. You could never tell that. You wouldn't be able to tell that. Yes, they'll always tell you what it is. Okay. Um, so part A, everybody's good on part A. When is it moving to the left, to the right, and standing still? Okay. But then part B says graph the velocity, and I'm just going to graph the velocity on the same graph. It'll just make it easier for me to see here. So remember, if I'm graphing velocity, and I'll put a V and T over here, that is derivative of position. Yes? Say again. Okay, well, here's what I think about. If he goes from position 0 to his position as at 2, he's moved to the right. So essentially, yes, you're looking at the slope of it yourself. Yes, yes. So he's moving right, he's standing still. This is decreasing, so he's moving left. Standing still, moving left. Because of the slope. But the slope is velocity, so yes. Either one, yeah. No, this one just said part B graph the particle's velocity and speed were defined. On the what? Yeah, it says graph the acceleration. And they gave you velocity. What? D on 11? Oh, is that when you weren't in here? Oh, look, it was. All right, here we go. Velocity. Yes, you ready? All right, velocity is nothing more than the slope of the position, right? From here to here, what is the slope? Positive what? Right? Agree, disagree? Rise over run, yes? So this is going to be from here. Is it included here or no? Why? It's a corner. I'm not differentiable at corners. Okay, how about this next part? 0. Again, not differentiable at corners here. There's that. How about this piece? -4. It's going to be down below, about right here. So, how about this piece? 0. How about this piece? -2 again. Oh, it wasn't. Yeah. We're not quite there yet. We're not quite, but we will be. Yes. But we'll get, yeah. Okay. We'll get there. That's right. So that's a good question, Anna. So now whenever they ask me about speed, how is the graph different? Well, the graph, the only thing that changes, right, is all my negatives whoop, become positive. Become positive. Yes. It tells me where my bug is at a certain time. Right. So this says if I'm looking at the pink one and I was at, let's say, 1.5 seconds, that's falling about right here, right? Where is, y'all can't remember the name. Where is Meriwether at 1.5 seconds? Well, she has made her way to position 2. So she'd be at 2, but she's just sitting there because she's being lazy for a couple seconds, right? That's what position is telling me. Right, right. Say again. 2 derivatives where? Talking about the white versus the blue. So this blue color or green color, whatever it is, this is velocity. Oops, I didn't mean that. Okay. This color, this is my velocity. Yeah. So that's just velocity. Whenever it asks me for speed, speed takes every negative velocity and makes it positive. So it'd be the exact same graph, but everywhere it was below, it just flips, it reflects it over the x-axis. Yes. That's absolute value of velocity. Yeah. Of velocity. You have to do the derivative. Right. Yeah. Here, the acceleration is always going to be what? Zero, because they're all lines. Yeah. Well, so she's going different speeds at different times. So at you're talking about graph the body speed for this. Yeah. They just wanted you to graph. They just wanted to tell you to take velocity and flip up any negative. Yeah, speed. Speed is velocity. It's just the absolute value of velocity. So, what is the speed of my Merriweather? The what? Yes, because she's not going at a constant speed as she moves. Right. Yeah, it'll say what is the speed of the particle at 1.5 seconds. Not unless it's constant. Yeah. Well, but I stopped homework to teach a little bit of new stuff and kept because we were running. No, I did that because I gave this out. Yeah. All right. Because I wanted us to be able to fully analyze these graphs as we went through. All right. So I'm assuming 18 now. Okay. I enjoy this particular problem. Zero is at a weird spot here. Zero comes in. This is my zero line here. So it does something like this. It comes down, and then it does this whoop. Okay, so this is 12. This looks like almost 11, maybe 10, and maybe they did say it was 11. Okay, about 11. This is at 2. Okay, this is, first of all, if I had nothing else, if I just had units, how could I tell what I was looking at? Feet per second. I'm in a rate. Rate of change, yes? Feet per second. So this is a what graph? Velocity graph. Okay? Very, very, very important that you understand what you're looking at. So if this is velocity, that means that is also the derivative of position. Okay? So I'm looking at a derivative graph is what I'm looking at. Everybody with me? All right. Use the graph to answer the following questions. How fast, now what does fast mean? Speed. So what is the speed and how does speed relate to velocity? Absolute value of velocity, right? Okay, so this is the graph of, and are they all, is velocity always positive for this? No, because Look, so this little piece, yeah. All right, so it asked me how fast is the rocket going at, oh, when the engine stopped. Okay, so can you all envision what's going on here? We blast off, right? You have to do that sound effect with it too. All right, the engine stops, right? It starts falling. What happens right here as it's falling? The parachute pops out, right? And it stops right, and it stops it from falling so fast, and it whoop, okay? Right. All right. So, how fast was the rocket climbing when the engine stopped? That's right. This is at about 190. 190 feet per second. If you do not do your feet per second, you do not get your point. Okay? Does it matter that you can get the right number? If your units are wrong. All right. What? What if you have to what? Sometimes you do, actually. That's why it's so important to do it. Sometimes they'll say, because they'll start you out, and part of knowing the units is understanding whether you're working with the original function, the derivative, or the second derivative. So if you get the units right, a lot of times they'll give you a point for that. And we'll get into FRQ breakdowns at what point for point what you get, but a lot of times you do. That's why I always say take a derivative, write the unit, do something, because there's so many stupid places you can get a point. Say that again. Divide what by 2 to 190? Tell me why you want to divide it by. It feels like you're supposed to. So because this is velocity, right? That means at this time, so this point is 2, 190. So if I think about the velocity at 2 seconds is 190, the y value is giving you your speed or your velocity. Right. Yeah. How many seconds did the engine burn? 2. How do you know that? This is where it stopped, right? So it burned and then it boop stops. And that's when it starts. Okay. Now, let me ask you this. Is the rocket falling here? No, it's not falling, y'all. It's still accelerating. If you think about it, if you shoot it off, right, it's still going up. It's slowing down. That's exactly what's happening. It's slowing down. It's not going up as fast. Why is it slowing down right there? Okay, give it to me in calculus terms. Why is it slowing down right there?
Because they don't equal each other. Different signs.
Not different signs, right? They're different signs. The velocity here is still positive, but my acceleration is negative, which means my rocket is still going up, just at a slower rate. Yes? Okay. Enough. Let's answer the questions they asked. How many seconds did the engine burn? 2 seconds. When did the rocket reach its highest point? And what was its velocity? So notice it's saying when. So when did it reach its highest point? Why it says at 11? Why is it 8? Remember, sign of velocity tells me the direction. I'm going up. I was down, but now I'm up. Okay. Going up.
Here we go. Here we go.
I'm going up. When I hit 0, that's when I start going down, right? So that's when the rocket starts falling. So still, rocket, the engine burns out, but I'm still going up because I've got all that force behind it, right? Then at 8 seconds, that's when I start falling. And I feel like this graph is a little confusing, like y'all said, because that 0 is kind of in the wrong place, right? It's not the bottom like I'm used to seeing, but that's okay. All right, this is such a fun problem to do. It would. It would. What was the velocity at that point? 0. Velocity is always 0 when I change direction. I didn't even have to look at the graph for that. I could have read that question and go, oh, yeah, because it has to be 0, because if it's at its highest point, then it's going from high to low, so it's changing direction. That only makes sense. All right. When did the parachute pop out? We already talked about that a little bit. 11 seconds. Not here when it changed directions. Going up, it starts falling. It doesn't pop out until 11 seconds, and that's whenever you see this shift in velocity, right? How fast was the rocket falling at that point? Okay, no, what's it asking me? How fast it was falling? Nope. Why 90? Why 90? This is velocity. I'm still on D. And we said at 11 seconds is where the parachute popped out. When it popped out, how fast was it going? And if you look over here, this is like negative 90. But because it's speed that I'm talking about, I can't. Right. So it's falling 90 feet per second. Yes? How long did the rocket fall before the parachute opened?
8 to 11.
Right. How long did it fall? Where did it start falling? It started falling here. Parachute pops out here. How long was that? 30 seconds. Yes? Okay, now we have to start being a little bit more intuitive. When was the acceleration the greatest? Why? That's what I'm looking. I'm talking about slopes here, right? When was the acceleration the greatest and when was it constant? When was it the greatest acceleration? Bless you. I'm talking about slope, yes? This is going to be my steepest slope. Agreed? Oh, yeah, it is. Sorry. The constant, that's right. You're right. Sorry. Great day. Yes. So this would be my greatest because my slope is the steepest. Right. So from 2 to 11, the slope is constant. Yeah. Yeah. All right. Yes, no, maybe so. That was fun. That was great. What right side? Okay, think about velocity. The sign of velocity tells you if I'm going up or down. So velocity here is positive, but from here to here it's positive, so it's going up. But from here to here, anytime actually from here to here, I'm going down because velocity is negative. That's speed. That's not direction, that's speed. Speeding up or slowing down. take a look at the white sheet I gave you. All right. I'm just going to keep going. If y'all need to go to the bathroom or do what you need to do, I'm going to keep going. All right, the graph of the position S of t of a particle along a horizontal coordinate axis here is given, and you've got this graph, and I was just going to project this up, but I decided not to you to join us.
I was here the whole time. Martin present. Never left.
But no, she marked me absent. I was 15 minutes late.
I'm sorry. I don't want to get behind.
Look at the graph here. The graph shows position. This time I'm looking at position. Notice the difference, right? Here we go. All right. When is the particle, and here's, you've got to really think about this because I got to think about what I'm looking at, right? When is the particle moving to the left? This is position. All right. I start at 0 seconds. Where am I? All those little stickies are gone. -4, right? It takes me 1 second to move where? To -2. Am I there? Close. Okay. And then what happens between seconds 1 and 3? Well, this is not speed, this is position. I'm just sitting there. And at 3 seconds, I'm still there. I haven't moved. I got a lazy bug. But then at 3 seconds, what happens? Between 3 and 4 seconds, she moves all the way up to, right? And then she sits there. She goes back. Not as fast.
There it is.
To -2.
She ran a little too fast. There it is.
Okay. To -2, right?
On the velocity graph.
If this was velocity, so what am I looking for here? What am I looking for? If I'm asked when it's moving to the left, what am I looking for? And use your red sheet too. Left means negative velocity, right? Which is the derivative of this one, so I'm looking for negative slope. So when am I moving to the left? Only one time did she move backwards, and that was at the very end, and that was right here. So when? So from 5, and I can't include 5 because what's happening at 5? Right. 5 to 7. To the right. From 0 to 1, because from 1 to 3 she's resting, right? And then from 3 to 4 she continues moving to front. It's hard because your brain starts getting all confuzzled about, am I looking at velocity? Am I looking at position? What am I looking at? Well, this is position. No, this shows the position of a particle.
No, that's position. Yeah.
When is the particle standing still? When is my bug just sitting there doing nothing? 1 to 3, 4 to 5. No, silly. This is just something for us to talk about. More with this. We camp out here for a little while. We are. If it's the graph of velocity. I think most of them we did was. They'll tell you which one it is. Like this one says the position of a particle. I know. That's why you really have to. All right. All right. I'm not going to go back over those graphs right there right now. 13, 16, 13, 14, 15, 13. Here we go. Ready? 13 from your homework. We've already done 3 of those graphs. I'm not going to take any more time to do that. What?
Wait, we didn't do our
Y'all don't know how to do these graphs? Well, it's just the slopes each time, yeah. What's the slope? Yeah. Yeah. 2 over 1, which would be 2. So from, okay, no positive.
Hold on, can you do it the next one?
Y'all, that's a positive slope right there. Right? So that means I'm at positive 2 from 0 to what?
Oh, it's that thing?
And yeah, then I'm at, my slope is 0 from 1 to 3. And then from 3 to 4, what's my slope? I go up 2, 4 over 1. So the slope is 4. Is that right? From up to 4. Is that right? And then 0 from 5 to 6, right? No, from 4 to 5, sorry. 4 to 5. And then from 5 to 6, it's negative, what is it, negative 4? Negative 2. No, it's not. Down 2, 4, and over 2. Negative 2. The only way that speed changes, the only way that speed changes here is this piece. Whoa, that's right. This piece, yeah, it is, sorry. This piece comes, where's 2? It comes up here. That's speed.
What's the difference?
Oh my goodness, y'all.
That was supposed to be.
And then when the particles moving from 3 to 4.
So that was the velocity.
The highest? Yeah, that's the velocity, but then the other one.
What is this, from 3 to 4? Why does it keep doing that? Yeah. It shouldn't be. It should be open. Sorry. Getting in a hurry over here. Should be at 2. Well, y'all hollered at me for not having written it in the right. What? All right.
No.
Okay, y'all know what I meant. Y'all know what I meant. Okay. Oh, but you did. Right. Yeah. Same page. Say again. Flip it and make it positive. Yes. Not the original graph, the velocity graph. Speed is the absolute value of velocity, not position. And I started with position on that one. All right. Lunar projectile motion. Here we go. This is where we don't have a graph. We just have an equation. We're going to have to do some analysis. A rock is thrown vertically upward from the surface of the moon at a velocity of 24 meters per second. Now, understand what this is saying. If you took physics, you understand about initial velocity. Okay? That means when it left my hand, it was going 24 meters per second. All right? So I will sometimes do a little v sub 0 that tells me that's initial velocity. That's all. This is it. All right, initial velocity, 24 meters per second. Reaches a height, and I'm going to do S of t. They don't have the t in there, but I'm going to do S of t because they should. 24t minus 0.8 t squared meters in t seconds. All right, here we go. There's the setup for the problem. You're exactly right, Slade. So if I need to find, it says, find the rock's velocity and acceleration as functions of time. So I just did the derivative. 24 minus, that's it, right? Wait a minute. Yeah, I'll give you a second. What are my units here? Velocity at any time, that's right. Velocity at any time is 24 minus 1.6 meters per second. That's right. And sometimes, until you get used to it, you might want to come over to the side and remind yourself. Position, the derivative of position gives you velocity. The second derivative of position is the first derivative of velocity, which gives you acceleration. So if I keep taking derivatives, I end up at acceleration. One more time with give me the jerk. You'll need it in a minute. Power rule. They didn't ask me. Now, does it make sense looking at that velocity equation? You asked, do I need the 24? But looking at that initial velocity equation, does it make sense that my initial velocity is 24? I'm getting there. What's at time 0, if I put a 0 in for t, what's my velocity? 24. The derivative here. Now, how do I find acceleration? I do the derivative of velocity, which is the same thing as the second derivative of position, and I get negative 1.6 what? Meters per second squared. That's acceleration. Okay. All right. Part. Okay. That was part A. Velocity was 24 minus 1.6. All right. Now we're going to, yep. Now we're going to start doing some analysis. When we do this, I like to do a sign chart. I always do a sign chart. It helps me so much, okay? I hope it helps you too. This is a non-calculator, actually. This will be a non-calculator. All right, so the first thing that it asked me is how long did it take the rock to reach its highest point? Now, I could use algebra, right? And I could say, well, this is a quadratic. I could just find the vertex of the quadratic, right? But we're not doing algebra. We're not doing this from an algebraic standpoint, calculus standpoint. So instead, opposite b over 2a. Okay, but calculus way is actually much easier. Now, think about this for just a minute, okay? And really think about this before you answer. If I'm looking for the point where it was the highest or lowest, the zero of what, Slade? Did you say zero? Well, he was actually right.
Zero of velocity.
The zero of velocity. But at that zero, I need to make sure what's happening. Changing? I didn't say that. I'll say it. Keep with that thought process.
Oh, wait.
Keep with that thought. Changing, not direction, but you're getting there. Keep going along that path. When velocity changes signs, this is crucial. When velocity, you have to, because this is how you have to justify. When velocity changes signs, a maximum or minimum occurs in position. This makes sense if you think about it. Well, how do you know? It's changing directions. You're exactly right. That's what it means, right? How do I know? Well, here's what I have to do. I have to say, okay, to find this, what I have to do first is set velocity equal to 0. I need to find those places, right? This is what I meant when I said we're doing it algebraically. I need to find those places where velocity is 0. Well, okay, that's fairly easy because I've just got a linear equation for velocity, yes? All right. Well, where does velocity equal 0? Okay. Normally you'll have something you can do in your head for something like that if it's not calculator. But here's the point that I'm getting to. All right. This is what I call a sign analysis here, okay? And we did some of this, and I can't remember if it was Algebra 2 or Pre-Cal whenever we were doing inequalities. The sign of velocity is going to tell me what position is doing, right? If velocity is positive, what am I doing? Going to the right or up, right? If velocity is negative, I'm going to the left or down. All right, so I know at 15, that's where my velocity is 0, but here's what I need to know. What's happening? Here's 15. Am I doing this? Am I doing this? or am I doing this? Okay, because that's gonna determine whether I'm a high, a low, or I'm just staying, just continue. Okay, but don't think in terms of algebra. Think in terms of calculus right now. All right. It maybe it could be an endpoint though. It could be that I started out at the highest point, and we'll get to that, or I ended after so many seconds at the highest point. Okay, so here's what I'm going to do. You're on the right track. I'm going to think, if I took a number, now I can't go below 0, right? I'm not going to go below 0 because time's not going to go below 0. I'm not a time traveler. I don't go back. What is the sign of velocity between 0 and 15? In other words, pick something easy. If I put a 1 in there, here's my velocity equation. If I put a 1 in there, is it positive or negative? Positive. That means if velocity is never 0, from 0 to 15, just it crosses over at 15, that means this whole time interval, I'm increasing, or I'm going up, or I'm moving to the right. Does that make sense? Yeah. Velocity is positive on that whole interval. Okay? Y'all with me? What's the, oh, yeah. Once I pass 15, right, if I plug in a number bigger than 15.
No, I mean, like, that part.
Getting really excited.
Because the more you multiply, the bigger the number you're subtracting from.
Right, but you're getting into acceleration. We're not going to get there quite yet, but you're right. You're right. All right, so from 15 on, right, so say I plug in 16, 17, 18, I'm sure you can guess what's happening, right? Negative. It's going down. So where is my maximum occurring? At 15. What is the maximum? No, that's the time it happens. At 15 seconds, what am I doing? I'm a lunar, a rock. At 15 seconds, my rock reaches the highest point. What is that highest point? Plug it into what? No. Position. If I say, I feel like it was a great revival or something, right?
I did that a second ago, right?
I love this stuff. I love this stuff. Yes. How long did it take it to reach its highest point? 15 seconds. Now, if you plug in, and you could use a calculator for this part of it. Yeah. What? Original equation, right. So for C, whenever it says, where did this happen? Will this happen if I plug in? So if it ever asks when, that's your T, right? If it asks how high or where, so when is T, where is your position? Okay, so I'm plugging into this. So if I want, I'm sorry. So if I want to know here where, excuse me, then I would plug 15. I would plug 15 into the position. That's the original equation. You should get 180, didn't you? It's 180. This one's meters. Now, what would happen if I did this and I got negative? What's happening there? Where would my highest point? It started at its highest point, right? If it's always decreasing, then I started out at the highest point. Does that make sense to you? Okay. All right. When did the rock reach half its maximum height?
7.5.
So half of its maximum height happens where? Not when, but where? Oh, we're halfway. which is 90 meters. So now, when does 90 meters happen? Not velocity. When is position? When is position? I mean, where is position? Where is position? Where does it happen? So how did you get that? No, you can't do that. No. That's not, no. So this would be a calculator. You take the original position. I'm always going back to that position when I'm talking about where. That's position. So where does this, it says when, so when where's the rest? Minus 0.8 t squared. When does it equal, what did I say? 90. How can I solve that? Well, I can take out my calculator and I can graph. Okay, now it's a calculator. I would graph to solve this. I would make it equal 0 and find where it crosses the x-axis. You should find that it crosses at about, is that what y'all got? And for the sake of time, I won't go through. But it should be an upside down parabola, though. Yes. Yeah. It better be. Well, the first part wasn't, but now it is. Because if I graph this minus 0.8 t squared minus 90 equals 0, to solve that for t, that would be where it crosses over. Where it equals 0. You did negative 90 instead of minus 90. 24x minus 0.8x squared. I got an upside down problem. Except for my parabola is situated more like this. Which makes sense. You put the minus 90, which makes sense because if you think about this rock, right? Yeah.
What if we don't get exactly like 4 points?
You have to round it 3 places. You will if you use your calculator. You will. It makes sense that it hits that position twice. Why? If I throw it up and it comes back down, then it hits that height twice. All right. I don't want to get bogged down in this too much longer. How long was the rock aloft? Because it's a constant gravity, that's right. Yeah, so 30 seconds in the air. All right, listen, I know this is hard, and this is hard. This is why we spend so much time on PVA and why we kind of eased in with the graphs. It is a lot. I'm going to adjust the homework a bit. Let me at least set up 21 for you. A particle moves along a line so that its position at any time is given by the function bleh, where s is measured in meters and t is measured in seconds. Find the instantaneous velocity at any time t. This is position, because if you ever see s or x of t, that's position. So how can I find instantaneous velocity? Take the derivative. This is a hard one to take the derivative of. I would probably expand this out before I tried to take the derivative so that I could just do power rule. Or you could do product rule, but you're going to be in a mess if you try to do product rule here, especially before we learn chain rule. T cubed minus 4t squared minus 4t squared plus 16t plus 4t minus 6. T cubed minus 8t squared plus 20t 16 what? And that's just power rule. So at the beginning, I couldn't do, we haven't quite gotten to chain rule yet. So, yeah. It would work on this one because the derivative of t minus 2 is 1, and it would work. But if that was a 2t inside, that wouldn't work. So now my velocity would be the derivative of this, right? And this is instantaneous velocity because anytime you do a derivative, it is instantaneous. That is instantaneous velocity.
Yeah.
What's the acceleration? The derivative of that. Do I have a constant acceleration this time? No. My acceleration is changing here. Yeah. When is the particle at rest? How do I tell when a particle's at rest? What equals 0? Velocity. That's where this page is going to help you, okay? It's at rest, so when you see at rest, you think velocity equals 0. This would be a factoring one. What multiplies to 60 but adds to 16? And 6. Multiply the first and the last together. Did y'all think factoring was going to go away? Okay, when I said when is it at rest, I need to know, how do I tell when it's at rest? When velocity equals 0. So if I set a quadratic equal to 0, how do I solve a quadratic equal to 0? I have a multitude of options. I could factor and solve. I could do quadratic formula. I could complete the square. I could graph and find the 0. Remember that whole unit we did in Algebra 2 where we spent like 5 million weeks talking about all the different. All right, so all I did was factor it. I factored it because that's the easiest for me. So when is my particle at rest? 10/3 seconds and 2 seconds. Do I know if it's changing direction there? No, I don't know right now. But I know he stopped. I know that bug stops at 10/3 seconds, and I know that bug stops at 2 seconds. What he does outside of that, I don't know. I could find out. How could I find out? I'm sorry. I'm trying to beat the bell. No. Not into the position. No. Into velocity. So never. I know y'all. I know. 2 and 10/3, right? The velocity is going to tell me what I'm doing here. If it's positive, I'm up or right. If it's negative, I'm down or left. That's going to tell me if I'm maxes or mins. Coach Hendricks is used to it, y'all. I'm sorry. He knows. You're home. Mm-hmm. Let's see if it's positive or negative. That's that sign analysis. Mm-hmm. Yes, that's when it's addressed. All right, guys, listen. We quickly forget that Miss McGee dismisses the class, not the bell, so y'all stay put for just a second. If I make you late, I will take responsibility for you being late. Now, for your homework tonight, what I would like for you to do is on pages 142 to 143, I'm going to cut this down from what it says on Canvas. Do 14, 16, and 22. We'll pick up the rest tomorrow. Y'all have a good day.